Good morning! Merry Christmas, everyone! December 25th. Wow, we've arrived at the last day of Advent of Code, and it's been a ride. When I started this out on the 1st of December this month, I hoped I would get to somewhere day 15, day 17, perhaps somewhere in the middle, but I never expected to get to the final day of the event and go through all of the days. So that's definitely been very interesting. It's been really fun as well, going through all the challenges, and I'm glad to have you here. Join me on Christmas Day to solve the last puzzle of our journey. We started at the North Pole on top of a mountain. We went down the mountain with a toboggan, and we arrived at the airport. We took our first flight to our first regional flight to our transit airport. We then took an international flight to a different island. We took a ferry, and then we had to reroute because of a storm. We arrived on an island. We took a shuttle bus to a different to an airport, and then we took another flight, and then this monster appeared over here, but we managed to escape it. And then from this island we took, I think there was yet another flight, so 4 flights in total, and then a high-speed train to the jungle. We built our own raft. We navigated the raft a few days over the ocean to arrive at the final destination, which is our tropical resort, and I think that's where day 25 is going to take place. So let's get into it. The way I do this, I read the questions out loud, and I I also think out loud, and I try to come up with a possible solution, and then I code it. All of this while thinking out loud. So if you have any questions of whatever I might be doing, feel free to ask in the chat. I'll be happy to explain. Also just let me know how you're doing today. Yeah. What time of the day is it there? Christmas just started for me. It's 10 a.m. in the morning, European time. So I had spent Christmas Eve yesterday with family. It was fun, lots of food as usual, and I am looking forward to spending another Christmas Day today after the stream, and tomorrow in the Netherlands here where I am. We celebrate first Christmas Day, second Christmas Day, and sometimes some people even celebrate the third Christmas Day. Yeah, it's definitely a highlight of the winter months. All right, let's start with day 25, the final day. It's called Combo Breaker. You finally reach the check-in desk. Unfortunately, their registration systems are currently offline. And they cannot check you in. Noticing the look on your face, they quickly add that tech support is already on the way. They even created all the room keys this morning. You can take yours now and give them your room deposit once the registration system comes back online. The room key is a small RFID card. Your room is on the 25th floor. Nice, up high. The view must be good. And the elevators are also temporarily out of service. We have to take the stairs. So it takes what little energy you have left to even climb the stairs and navigate the halls. You finally reach the door to your room, swipe your card, and beep, the light turns red. Oh, that's a problem. Examining the card more closely, you discover a phone number for tech support. Alright, we call tech support. So what are they going to say? Have you tried turning it on and off? Hello, how can we help you today? You explain the situation. Well, it sounds like the card isn't sending the right command to unlock the door. If you go back to the check-in desk, surely someone there can reset it for you. Still catching your breath, you describe the status of the elevator and the exact number of stairs you just had to climb. I see. Well, your only other option would be to reverse engineer the cryptographic handshake the card. What tech support says that? Cryptographic handshake the card does with the door, and then inject your own commands into the data stream, but that's definitely impossible. You thank them for their time. Unfortunately for the door, you know a thing or two about cryptographic handshakes. We do. The handshake used by the card and the door involves an operation which transforms a subject number. To transform a subject number, start with the value 1. Then a number of times call the loop size. Perform the following steps. Set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by this number, which is 2020 and then 1227. I wonder where the 1227 comes from. Or maybe it's random. The card always uses a specific secret loop size when it transforms the subject number. The door always uses a different secret loop size. Okay, so the cryptographic handshake works like this. The card transforms the subject number of 7 according to the card's secret loop size. The result is called the card's public key. The door transforms the subject number of 7 according to the door's secret loop size. The result is called the door's public key. The card and door use the wireless RFID signal to transmit the 2 public keys, which is the puzzle input for today, to the other device. Now the card has the door's public key and the door has the card's public key. Because you can eavesdrop on the signal, you have both public keys but neither device's loop size. The card transforms the subject number of the door's public key according to the card's loop size. The result is the encryption key. So this is like public key asymmetry. You have 2 public keys and then a certain loop size is used to arrive at the encryption key, which we don't know. The door transforms the subject number of the card's public key according to the door's loop size. The result is the same encryption key as the card calculator. Okay. If you can use the 2 public keys to determine each device's loop size, you will have enough information to calculate the secret encryption key. That's correct. That the card and door use to communicate. This will let you send the unlock command directly to the door. For example, suppose you know that the card's public key is this number. With a little trial and error, you can work out that the card's loop size must be 8. Because transforming the initial subject number of 7 with the loop size of 8 produces this number. Alright, then suppose you know that the door's public key is this number. By the same process, you can determine that the door's loop size is 11 because transforming the initial subject number of 7 with the loop size of 11 results to this number. At this point, you can either use the device's loop size with the other device's public key to calculate the encryption key. Or either device's loop size works. Transforming the subject number of this, the door's public key with the loop size of 8, which is the card's loop size, produces the encryption key, which is this number. Transforming the subject number of this, the card's public key with the loop size of 11, produces the same encryption key. Interesting. So what encryption key is the handshake trying to establish? Alright, let's get our puzzle input, which is really short for today. I'm just going to copy it and I'm going to create a new create a new file here, call it input.txt, paste it in there, and I already have the setup code from previous days in here to read our file. I'm gonna go back and reread some of the things because it's still not clear to me exactly what's happening here. So I'm gonna go through it all quickly. So this is all story, right? Transform a subject number. Okay, so to transform a subject number, start with the value 1, then a number of times call the loop size. Perform the following steps. Set the value to itself, multiply by the subject number. So if subject number is 8, it's going to be 8 times 1. And then set the value to the remainder after dividing the value by Oh, I see. All right, so that's going to be a math formula we're going to add into our loop. We don't know the loop size. The card always uses a specific secret loop size when it transforms a subject number. The door always uses a different secret loop size. All right, so cryptographic handshake works like this. The card transforms the subject number of 7. According, why 7? Is that just like an example? I guess so. According to the card's secret loop size, the result is called the card's public key. The door transforms the subject number of 7 according to the door's secret loop size. And then we have the door's public key. And then the card and door use the wireless RFID signal to transmit the 2 public keys. It's going to be the puzzle input. So we have the card and the door's public keys in here. Now the card has the door public keys and vice versa. And then using the door's public key, the card, and the card's loop size, you get the encryption key. All right. Hi from Eindhoven. Hi Wilfred Mayboom. Nice to have you here. Eindhoven is about an hour and a half from Amsterdam, 2 hours perhaps with the train, which is very close, 100 kilometers or so. For the people in the United States watching, that's very close, I guess, because distances in the Netherlands are small compared to the US. The card, and then so we have what we need is we have 2 public keys, and we need to get the other device's loop size to calculate the encryption key. And which it says here, you can use the 2 public keys to determine each device's loop size. You have enough information to calculate the secret encryption key that the card and door use to communicate. For example, suppose you know that the card's public key is 5. Alright, with a little trial and error, you can work out that the card's loop size must be 8, because transforming the initial subject number of 7. Okay, so we start with 7. We go through with the loop size 8. This is okay. So I guess I don't know why 7 though. It's not really clear to me that that's what we should start with. Subject number. Yeah, so they use 7 as the subject number in this example. But do we know our subject number for our own input, or is it still 7? Let me reread that to make sure. To transform a subject number, start with the value 1 from the following steps. Set the value to itself multiplied by the subject number. 7. Remainder, right, works like this. Okay. 7 is in bold. Okay, I'll just assume the subject number is 7. Good. Let's parse our input really quick here. We call this public keys. It's going to be input splitted by a new line. So we're going to have an array with 2 elements. Same question. Yeah, right. It's not really clear, but because 7 is in bold, I'm going to assume it is, because usually the stuff that's the text that is a little bit white, highlighted white and bold, is a clue to the puzzle and have special meaning. And so therefore, like here, subject number, loop size, and this number, they are a clue. So usually numbers aren't highlighted if they don't mean anything special. So like for example here, these are just examples. But here we know, here we can also see that the doors loop size is 11, and that's also highlighted. Although I think the loop size for our input should be different though. Yeah, not sure now. Now I'm doubting as well. It's I mean, because if 7 is not the subject number, if we don't get the subject number, maybe we don't get the subject number, and then we need to calculate ourselves. I'll have to think about this a little bit. So now you can use the two public keys to determine each device's loop size. You'll have, if I have the loop size, I have enough information to calculate the encryption key. So I need to calculate the loop size. And if we get the subject number, then we can calculate the loop size. Because we start with the end, we start with the public key, and then we can go backwards a number of times of a loop size until we using the subject number until we reach 1, and then we're gonna have the loop size. So we do need a subject number as far as I can tell. So the card's public key is this. With a little trial and error, you can work out that the card's loop size must be 8. Because transforming the initial subject number of 7 with the loop size of 8 produces this. Yeah. And then at this point you can use either device's loop size with the other device's public key to calculate the encryption key. So once you have the loop size and a public key of the other device, then you can then the public key becomes the subject number, and then using that loop size you produce the encryption key, and the other way around. So maybe there's a way to calculate this without the subject number. I'll have to write it down because it's a mathematical equation that needs to be solved. I could write it down. No, that's no worries. You're not disrupting my train of thought. You tried it with 7 but didn't get the right answer? Okay, so that might be a clue for me that that's not the subject number. What encryption key is the handshake trying to establish? And we get 2 public keys. I'm gonna maybe write out the math. We don't need any example here. Let's make this smaller. Math. Okay. So there's going to be a loop. Okay. So we always start with 1. That's a given. Start with the value 1. Okay. And then multiplied by the subject number, so we'll call subject number x, and then set the value to the remainder. So I guess we use modulo 2020 1227, and this is between parentheses, and then we do this kind of like, and then we get to, I guess x should be our result, and let's use this y. And then x is going to be our result, and then x is kind of like the public key. So after we repeat this a certain amount of times, yeah, this is tricky to like notate in maths. I'm not very strong in maths. Not sure how you rotate a loop, how you write a loop in maths. I think you use the sum operation. No, that's the sum. But okay, so regardless of that, we do this a certain amount of times, and then we get an X, and X is the public key. So we do this certain repeats Z times, repeat Z times, and then for the let's say the above was the card, and then we do the same thing for the door, and the door is going to have the same subject number, is going to have a different result. Let's call this X2 and X1. Repeats Z 2 times to arrive at a public key for both, and then we can use either one's loop to calculate the encryption key. It's going to be the same. So you can use either device's loop size with the other device's public key to calculate the encryption key, transforming the subject number of the door's public key with the loop size of 8 to the card's loop size, produce the encryption key. Alright, so we also know that 1 times it's going to be, so for the card, let's say card here, door there. So we also know that 1 times X2, what eventually is X2, modulo 2021-227, is going to lead us to encryption key, which is our final, let's call this W, repeats, and this also repeats the same amount of times. And the same thing for the door. If we use the card's public key as a subject number, we're going to arrive at the same encryption key, and then we have to do that the same number of times as the loops. Okay, so where Y is subject number, Y is subject number, X1 is public key card, X2 is public key door, Z1 is loops cards, Z2 is loops door, and W is the encryption key, which is what we are looking for. Okay. How many unknowns do we have? Z is unknown. We get the public keys. So do we know which key belongs to each device? I guess the first one is the card, the second one is the door. Puzzle input. The card and door use the wireless RFID signal to transmit the 2 public keys to the other device. I'll just assume the first one is the card because they start with the card. So we know that the card's public key is this number, and let's use example input. That's easier. We're gonna use that to debug anyway. So that's the card's public key, and what's the door's public key? It doesn't really tell us. Not here. All right. So that's what's known to us, X1 and X2. What unknown variables do we have? The subject number. That's either 7 or unknown. unfortunately it's not important. No, that's not really important. That's correct. X2 is the X1 and X2, and a W is an unknown, and then the loop times are also unknown. But we can do this with trial and error. We can start with 1, we can go upwards until we find a solution for, I guess, let me see. Oh yeah, this is clear to me right now. Yep. We have this formula where we have only one unknown, a second one, but a second one we can do. We can figure out with trial and error. So we need to solve for this, where this is equal to x1 is equal to this, and then we just loop as many times until we find a y that matches that. Is that correct? I could start. Let me see. I can't start at the end. Well, I can start at the end. I can just say loop size 2, start at the end, go back to 0. If the end result is not 1, then because I know, yeah, I'll know. Okay, I think I can make this work. I think I can use a while loop to so what do we, the value to itself multiplied by the subject number, and then the value to the remainder after dividing the value by, so 1 multiplied by subject number, set the value, the same value, perform the following steps. No, that's the different steps. Okay, so 1 multiplied by subject number, and then the value, the whatever comes out of here, the new value to the remainder after dividing the value by, all right, and then we're gonna have a new value. So this 1 is not static, it changes each loop, and then we use the new value in the next iteration and we multiply that by the subject number and so forth. So we need to solve for, I'm thinking of an approach where I'm looping backwards from like 2, 1, 0, 3, 2, 1, 4, 3, 2, 1, and so on. And we have our public key, we have this number. We need to solve for when eventually this value reaches 1. But we don't have y. We don't know the subject number. But there must be a trick to this, because no, I don't think that approach will work. Let me think of something else. So we know that when we have the public keys of both, that they can be the subject number. So what if we try something else? We know that when we use the public key of the other device, so let's say here we use the door's public key, and we already have that, and we know it's 1. we start with 1. So we have all the known variables here. We just don't have W and we don't have the loop. What if we the loop needs to be, it's different times. What if we calculate this several number of times and then we do the same thing for the door using the card's public key different number of times, and at some point with trial and error we should find 2 iterations that match the result, that have the same output the same result, which is going to be the encryption key, but the index or the iteration number at which they happen, that's going to be the loop sign, and those are going to be different for the card and the door. I'm just thinking the loop size, I'm pretty sure the loop size is not something small like 8 and 11. Maybe something bigger for our own input. Maybe not that big. I could store the results in an array. Thinking what the best way is to approach this. Because I should keep going on until I find a match. Yeah, let's do that. I'm gonna program that. Do I want to know if I should assume 7 as the subject number? I don't think 7 is the subject number. I'm gonna try an approach. I'm gonna try and calculate this and this. So I'm gonna try and calculate the possible encryption key for the card and the door using the other device's public key, and I'm gonna do this X amount of times until I find an answer, until I find that an encryption key that matches both equations, if that makes sense. So let's store, we're gonna say let's we're gonna say public key possible encryption keys card. We're gonna do the same thing for if I do get stuck with this solution, with this approach, I might need a hint, Wilfred, so I would gladly appreciate it if you stuck around for that moment. Hopefully not, but I think this should work. I think this approach should lead us to the correct answer. Hopefully the loop size are not too big, because the program is going to take a while then to figure it all out, because it's not very efficient. It's trial and error, but they're saying trial and error in their puzzles, so I guess might be a hint to that we need to use trial and error as well. So so we're gonna have the results here. Let's first compute the results. So const possible encryption key card is so 1 times public key card, public key it doesn't matter which keys for the card or the door, and that won't really mess up with our calculations, because we're using the other's public key. So if just the variable naming is wrong, if the first one is the card, the door instead, then the public we're actually calculating here the possible encryption keys of the door, not the card. But that won't really matter, because we're gonna end up with an encryption key eventually, which is the same for both. So just so that I can give them a variable name that is descriptive, I'm going to assume the first one is card. And I'm going to use the public key door and public key door, a modulo 2020 1227. We can hard code this, and and do the same thing for door. And we are using the remainder, aren't we? Set the value to the remainder after dividing the value by, okay. So that's gonna be this. And then we're gonna have to use this in the next iteration, I think. Right. Public key. The card's loop size must be 8 because transform the initial subject number of 7. Okay, but so here, transforming the subject number that with the loop size of 8 produce the encryption key. This should be the same. Okay, so we reuse that. So we'll have to yeah, we should kind of like start with, we're gonna need a variable here. We're gonna call this let loop size, starting with 1. And then we're gonna increment this loop size, and then we're gonna use, I guess I could start by 0, and we're going to maybe start with how is this a neat way to do it? 0, 1. I guess I could instantiate this arrays with the public keys from the other device, and then I could reuse them here by just tapping into that array. It's gonna be loop size, and we do the same thing here because we're reusing the value from the previous iteration. That's what we need to do here. Keys, and then as soon as we have those values, we push them to the array. So possible encryption keys card, push possible encryption key card, and then copy this to do the same for the door. Okay, so we are doing the math here for an infinite amount of times, if I'm not mistaken. And then we also need to figure out if at some point we get a value in here that also appears in here. So I'm just gonna say, well, this is true, or it doesn't have to be true. I can say const encryption key. An encryption key is going to be equal to possible encryption keys card find possible encryption key cards equals, Let me put this on a new line so we can read it. Equals or includes, I guess I can do that. I can do possible encryption key store. Key store includes our current value. If we find it, then we have our encryption key. So while there's no encryption key, keep going, and we're gonna try and find an encryption key after every iteration. So we just can copy this. So what this does is we're going through each element in the possible encryption keys for the card, and we try to find that element in the possible encryption keys for the door. And if we find it, then we can assume that that's going to be the encryption key. So we store that, and then eventually we have we can also figure out the loop sizes. What's the answer for the first part? What the encryption key is the handshake trying to establish? Oh, so just the encryption key. You could eventually also get out the loop sizes, because you can just figure out at what index the encryption key is in this array and in this array, and that index is going to be the loop size for both the cards and the door. But I'm just gonna use, but we don't need to do that. So maybe okay, moment of truth. Let's try it out. No idea whether this will work. Index.js. Assignment to constant variable, always do that. It's running, taking a long time. Let's add a breakpoint conditional 1 when loop size is, when we've done what, let's say 100, no, 1,000 loop sizes, 1,000 iterations. Okay. What do we get? Possible encryption keys. Oh. Okay, these are strings. These need to be mapped to a number. Okay, so possible encryption keys card. There we have it. Still, that's weird. We get the same result. Public key card, public key door. Yeah. There's a bug somewhere here. 1 times that number, and then the remainder. It's gonna be the possible encryption cards, key card, and then we push that at the end of the array. We do the same thing for the door, and oh wait, that makes sense. Yeah, because well, that doesn't make sense. So if we do, oh yeah, the 1. Okay, so 1 is not fixed. 1 is to transfer subject number, start with the value 1 and set the value to itself multiplied by the subject number. Oh, this is definitely a question of reading correctly, because I'm getting confused. Nazar says actual input takes some time, but example is fast. Okay, thank you for that hint, Nazar. Appreciate it. I might use the example input here just to, yeah, new file, input text, I'm gonna work with the example input. What's the, suppose you know that the card's public key is this number and door this one. All right, let's work with it. Example input, that's gonna be easier. Yeah, so here I'm not reading correctly. That 1 is not static. To transform a subject number, start with value 1. Then a number of times call the loop size, perform the following steps. So we start with 1 and then set the value to itself. So 1 is 1 multiplied by the subject number. So you multiply 1 by the subject number and then modulo that, and whatever the remainder is going to go into the next iteration, and we use that in the next iteration. All right, oh, I see. Okay, so this needs to be here we need to start with 1. We're starting with 1 here, and this is going to be here, and then multiplied by the public key door. Right, that's what needs to happen. And here, same thing, but the card instead. Okay, so let's run it again. That's not correct. Debugger, disable, enable, nope, disable. I'll just remove it actually. Okay. So after our first iteration, we have also before our first on a second with exits, because for some reason it finds a, oh, because 1 is in there. Okay, 1 is definitely not the encryption key. So how do we exclude 1 from, how about I just not have it there, and then here, if this is undefined, then I don't want. Okay, cool, that all makes sense. So possible encryption keys, nope. After second part, we have those. Second loop, we still get the same numbers. So what's going on? We multiply, we should probably because it's tapping into, oh, I see what's going on. Okay, so loop size needs to be 0. We tap into 0, there's nothing there. How about loop size? Not loop size, but loop number. I'm gonna rename this variable, not describing what it does. Loop number, and then it needs to be -1. Because we need the previous one, and we start at 1. Okay, let's try this again. First iteration, nothing there. Okay, second iteration, we should get different numbers now. Nope. So what's loop number here? Loop number is 3. So 3 minus 1 is 2. I have an off by 1 error again. Okay, so how do we make this clear? I started 0, I started 1, and we need to get the first. There is no first. So do I do -2 perhaps? Because on the second iteration, when loop number is 2, we need to get the first element, so that's going to be at index 0, so 2 minus 2. Maybe that'll fix it. It's a bit confusing, I must admit. It confuses me at least. Great, you get different numbers. That's awesome. So does this run? It runs. That's the encryption key. Good. Let's run it with our own input. Nazar Chop suggested it might take a little while. Otherwise, I'm really... Yeah, we're doing this by trial and error. We have a find in here with another includes inside. Might be slow. Multiplication, remainder. It should be fast. Pushing to an array should be fast because we're adding an element at the end. So we're not modifying the entire array. And then whoa, this does take a while. 1 minute and 4 seconds. But we did get a number. I'm just gonna try it. Too high. No. Probably because my math is wrong. I should have logged the So what encryption key is the handshake trying to establish? Yeah, that's we got the correct answer for the example input. Why is it giving us a wrong answer for the for our own input? I think this is our input, right? Copy pasted it correctly. Yeah, just making sure. Example input is this. Example input calculates instantly, and we do get a number, and then encryption key, find, let me add a breakpoint here at the end and see what we end up with for the example input. So these are all possible encryption keys. So we go 10 iterations. That's because, well, we go 11 actually, because yeah, that's because the loop size of the door is 11. So we go 11, and then we get this number here, which is gonna be in here because that's loop 8 for the card. 7 plus 1. Yeah, this makes sense. This makes sense. Encryption key, because we find it. So it told us the example input is, or the answer is too high. Is my math wrong? We grab the previous number. From card and door, yeah, and then we multiply that by the public key of the other device. So for the card that's door, for the door that's card, and then we set the value to itself multiplied by the subject number, and the subject number is the other transforming the subject number, the card's public key, with a loop size of 11, produce the same encryption key. Yep. And then set the value to the remainder after dividing the value by, so modulo that, and the remainder is going to go into here, and we push that to the array, and we're going to use that in the next iteration. That's interesting. I can't spot a bug here, and then we try to find the encryption key. We don't even need to find it here. Then I try to find it. And I'm gonna move this up top. Let's start this at 0. And I'm gonna run it with own input, perhaps 100 times. And let's see what's up. Possible encryption key. So we have a bunch of numbers here for the card, and the same thing for the door. These look pretty okay. The 2020 1227, this is hard coded, right? Yeah, that's gonna be the same for our input. And then, yeah, let me just remove breakpoint and go on. Gonna wait a minute again, because I have a breakpoint here. It's gonna stop when we have an encryption key, and I want to look at the arrays and at some values. In the meanwhile, so on the first iteration, this is going to be 1. 1 minus 2 is going to lead us to undefined, so then we're going to start with 1. On the next iteration, this is going to be, loop number is going to be 2. 2 minus 2 is 0, which is defined. It's the previous value. So we grab the previous value, we multiply that by the subject, set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by, and then set the value to itself multiplied by. Okay, so the program finished. We did a 6,213 loops, and therefore we have 6,213 possible encryption keys. And the encryption key that it found is 4136561, which is too high. Interesting. The public key of the card, it doesn't matter, but public key is that, and another public key is that. I didn't get this before. That's really weird. It's weird that it passes the example input, but it doesn't pass our own input. And usually we don't get that too often. And we get a result, but it's too high. But I have no idea what. I mean, what. Yeah, it could be an arbitrary number that's lower than that. Encryption key. I'm trying to see if my math is correct. But it would be weird that the math is correct for the example input, but not for our own input. But maybe there's an edge case here which we are not accounting for. 2020 1227 remainder. Set the value to itself multiplied by the subject number, which is what we do here. Inside here. So we get the value and then we'll multiply by the subject number. And then set the value to the remainder after dividing the value by, so I guess this is the new value, right? Or is it the same? Oh, this question is written really confusing. Set the value. What value? The handshake used by the card and the door involves an operation that transforms a subject number. Okay, transforms is in bold. Maybe I need to pay attention here. Transforms a subject number. To transform a subject number, start with the value 1. So our subject number is the public keys door, and then we start with 1. And perform the following steps. Set the value. Value is 1. Value is 1. Start with value on. Set the value to itself multiplied by the subject number. Set the value to itself multiplied by the subject number. I mean, that's correct, because we, at least for example input, we got 8 iterations for the card, we got 11 for the door, we got the encryption key that matches both. So the card transform, let's see, so the card always uses a specific secret loop size when it transforms the subject number. The door always uses a different secret loop size. Let me see, the card, transforms the subject number of 7 according to the card's secret loop size. To transform a subject number, start with the value 1. Wait. No, yeah. Multiply by the subject number. Works like this. The card transforms the subject number of 7 according to the card's secret loop size. The result is called the card's public key. The door does the same thing. With the door's public secret loop size, the result is called the door's public key. Transmit the 2 public keys to the other device. Now the card has the door's public key and the door has the card's public key. Because you can eavesdrop on the signal, you have both public keys, but neither device's loop size. The card transforms the subject number of the door's public key. So, according to the card's loop size, so the card transforms the subject number of the door's public key. According to the card's loop size, the result is the encryption key. This got me confused. The door transforms the subject number of the card's public key according to the door's loop size. The result is the same encryption key as the card. If you can use the two public keys to determine each device's loop size, you will have enough information to calculate the secret encryption key that the card and door use to communicate. Let me see. What if... Okay, so the encryption key, right. So for example, suppose you know that the card's public key is that number. With a little trial and error, you can work out that the card's loop size must be 8, because transforming the initial subject number of 7 with the loop size of 8 produces that number. Maybe the subject number is 7 that we need to use. Or maybe not. But here they say with a little trial and error you can work out that the card's loop size must be 8, because transforming the initial subject number of 7 with the loop size of 8 produces that number. Let's try and if we change the subject number to 7, we should get the public key at some point. I'm gonna do that really quickly in a different loop. I'm gonna do that const let result. Well, result is not equal to, what's the public key? Public key card, right? Let values gonna be an empty array. You're gonna tap into values here. You're gonna use the 7 as the subject number, and then we're gonna get rid of this. This is public, right, value, it's fine. Push the value in there. So I'm just going to do this for the example input. Bug. Where's the error? All right. We are doing something wrong here. Loop number. Oh, because there's no loop number. We actually do need the loop number here, and we do need to increment it. Right. So has already been declared. Oh, let's call this 2. Still doesn't work. Values, value push value. Define, start with 1 times 7. The push value there, and then okay, so result equals value as well. Maybe that's what we need to do. Right. Okay, so let me add a debugger here, a breakpoint, I mean. So we have values until we get to 576480101. We looped 8 times, and then we get to public key. So maybe we can do the same for our own input. And I'm going to comment out all of this. encryption key. Well, yeah, I don't. Wait, breakpoint, debugger. So what is, okay, so what does values look like? Values. Oh, we get a ton of values. How many loops? That's a ton of loops. 17 million. Yeah, that's, no, subject number is not 7. Pretty sure of that. Or maybe using 7, because it found here with 7 it did find a public key that matches that. So now we have the loop size, I guess. Loop size, rename loop size card. So I'm just gonna try this approach then. It's very confusing that I don't know what the subject number is. Yeah. But with using subject number 7, we get a loop size of this big number, 70 million something for the card. And we need to do the same thing. We don't need to do the same thing. Now that we have the loop size for the card and that we have the subject number or the public key of the door, we can calculate the encryption key, right? Yeah. So while loop size card is, I guess, so we need to do a certain computation this amount of times. So let's say encryption key, and then we're gonna have to do kind of like the same things here. No, value loop size cards -2 because we start at the end. Wait, what did it say here? At this point, you can use either device's loop size with the other device's public key to calculate the encryption key, transforming the subject number of the door's public key with the loop size of 8, the card's loop size, produce the encryption key. Okay, so this needs to be public key card door. Oh, the key door. Okay, and just from the subject number of with the door's public key. Oh, so that's the door's public key. Yeah, with the loop size of 8, with the loop size of whatever we found here. Produces the encryption key. Okay, so we should get our encryption key at the end. So let's have this encryption key here. Kind of just do it like this. Oh wait, we need to actually use the, let's fine. Values too. I'm just doing this really quickly without descriptive names because I'm just trying to see if subject number 7 is indeed what we need to use. And then I'll refactor later. So yeah, I'm using that here. Encryption key. So we have our. So here we're calculating the loop size of the card, and then we use the loop size of the card and the subject number of the and the public key door, which is the subject number. And here we use that value. That's good. This value push it there. Loop size card we go down. Okay. I'm gonna give it a spin. We get 523731. Is that using, wait, let's use the example input. We get a different number. We should get the encryption key. So maybe we're off by 1 here. Let me just think. I'm gonna add a breakpoint here. So loop size card is let's stop. Okay, loop size card is 8. So maybe let's see 8 and then 7, 6, 5, I guess 4, 3. What's the encryption key? It's values too. Oh, that's weird. So how do they do the transformation of the encryption key? At this point, you can use either device loop size with the other device public key to calculate the encryption key. Transforming the subject number of, which is the door's public key, that's correct, public key door, with the loop size of 8, the card's loop size, card's loop size, produces the encryption key 14897. So we start off with this, we start off with 1, we multiply the public key door, we get the remainder, which is that, and then, oh, I see what's going on. The loop size card should be we're going backwards. Okay, so we need to actually increment this, but we need to increment let's see, no, let's say iterate, let's just say I is loop size card, and then we're gonna say I minus minus, because we need to go down, or no, wait, I is 0, while I is smaller or equal than loop size card, multiply add, yep, okay, let's try it again. Yep. So we're getting same value. That's weird because, oh, I forgot to use I in here. So now we have, right, now we have different values until we reach the, yep, encryption key. Oh, it wasn't there. Just the encryption key. Oh, we're off by 1. Okay. guess smaller than, or I should start at 1. And then we have the encryption key here. Well, yeah. Let's run it again. Should start at 0 really. And loop size card. Do it at the end here. Plus plus. Start at 1. I'm off by 1 somewhere. Yeah. Okay. So that gives us the answer for using the example input. Let's use the our own input. Then we know if the, so we do get a different number here. So subject number was 7. God. But we did it. First part, we got the star. So, okay. Right. I'm gonna refactor this a little bit because this is indeed the correct answer. Yeah, that was really confusing. Frustrating. Okay, so we found out that we had to use 7 as the subject number, and so we could hard code it, and because we know the subject number, we could calculate the loop size of either the card or the device or the door, and then when we have the loop size, we can calculate the encryption key using the other device's public key, which is what we're doing here. Okay, so well, I might refactor this after the stream. So part 2. Oh yeah, Wilfred, you were watching all this time knowing that the subject number would be 7, and I was like here trying to figure this all out, trying to be clever, be like, yeah, sure, if we find a match in the possible encryption keys, then that should be the encryption key. But this, knowing that this was all wrong all along. Oh well, that's good. I didn't want help, so it's that's on me. Okay, second part, let's go on with it. The light turns green and the door unlocks. We got into the room. As you collapse onto the bed in your room, your pager goes off. It's an emergency. The elf calling you explains. The soft serve links to a Wikipedia page. What's soft serve? Oh, machine, nice, ice cream. Like it. We call this soft ice cream in the Netherlands. Yeah, soft ice cream. Soft serve machine in the cafeteria on sub's basement 7 just failed, and you're the only one that knows how to fix it. We've already dispatched a reindeer to your location to pick you up. No, are we going back to the North Pole? We just arrived on our holiday. You hear the sound of hooves landing on your balcony. The reindeer carefully explore the contents of your room while you figure out how you're going to pay the 50 stars you owe the resort before you leave. Noticing that you look concerned, the reindeer wanders over to you. You see that it's carrying a small pouch. Sorry for the trouble. A note in the pouch reads, sitting at the bottom of the pouch is a gold coin with a little picture of a starfish on it. Looks like you only needed 49 stars after all. You don't have enough stars to pay the deposit though, you need 2 more. Although it hasn't changed. Oh, I guess I cannot finish the last part because I haven't finished. Is that correct? Whirring Wheels, thank you for following. Off topic, I like the background music. So the background music is, I'm using Stream Beats, which is copyright free music for streaming. And the particular playlist that I'm using is, if you go to streambeats.com, they have, I think it's, what's the author's name? I think his name is Helen Harris or something like that. He has several playlists, genres, and the particular genre that I'm playing is synthwave. and you can download them or listen to them on Spotify. So yeah, that's the music I'm using in the stream. So I guess because I don't have, because I haven't completed all the puzzles, I cannot unlock the last one. So I need to complete the get this star and this star as well to get the last to unlock this. That's a shame. I did not know that. Need to get all the previous stars to yeah. I thought I could just I thought the second part would be unlocked, and then I could finish off these two after the event ends later on. That's a bummer, because I know 23 I need to make a linked list, and I didn't have time to do that to optimize the approach from part 1. Arrays took too long to compute, so I had to create a linked list and use that. And for day 20, that was the monster in the puzzle. So here I actually needed to calculate the map, or like to compute a map and find the monster and so on. So yeah, I haven't completed those yet, so that's unfortunate. It seems like we won't be able to do part 2 today. I might do another stream later on. So what I'm going to do, I'm going to solve part 2 of days 20 and 23. And then I'm going to do another stream of day 25 with the second part. And that's probably going to be somewhere next week before year's end. Because I do want to stream the second part of day 25. That would be cool. Because I'm really curious about the twist of the second part for today. Because we calculated the encryption key. And maybe we're gonna have to use the encryption key to fix the soft serve machine in the North Pole, or maybe not. Maybe it's part 2 something different, completely different. We'll have to see. But I think I'll have to wrap the stream up. Yeah. Well, thank you for keeping me company, Nizar Wilfred. There's no second part for 25. Because looks like you only needed 49 stars. Oh, I see. Because, right, so the whole purpose of this year's Advent of Code was collecting 50 stars to pay the deposit for the room. But, sorry for the trouble, a note in the pouch reads, sitting at the bottom of the pouch is a gold coin with a little picture of a starfish on it. Looks like you only needed 49 stars, so we get 1 star from the reindeer, which is part 2. So part 2 is, there is no part 2 for day 25, because the reindeer gave us the star, so there's nothing left to solve. So I only needed 49 stars to complete the event. So which is, yeah, those are the 2 stars that are missing. And then I guess, yeah, right, there won't be a stream of part 2 day 25 because there is no part 2. I will finish off, I'll collect the 2 more stars that I need to get to reach 49, and then I think I'll have solved the I've collected all the stars, and then probably something's gonna happen with the map. It's gonna say, hey, congratulations for finishing. Yeah, very short stream. Yeah, all right. Well, I guess that's it. We can conclude. But yeah, first part, maybe I'll spend some time refactoring this. Yeah, I'm gonna spend a little more time refactoring this, and I'm gonna make this into something more readable. And I'm going to then push the answer for the first part into the repository. I'm gonna link it in the chat in case you wanna have a look, or if you're watching this on YouTube later on, it's gonna be in the description below. But this is the repository where I've been storing all the solutions for Advent of Code of this year. And it's all in JavaScript, obviously. I haven't used any third-party libraries just native methods and native modules from Node.js. Actually, the only modules I've used was the file system to read the input and the path. And outside of that, I haven't used Lodash or any helper functions or whatever. So that's neat. That's something that I wanted to achieve with this year's Advent of Code. I didn't want to resort to using other libraries to like make that have a linked list, for example, implemented off the bat, or I wanted or like certain lookup. A few times I had two arrays and I had to look up I had to intersect the arrays and get the values that appear in both arrays. And Lodash, for example, in JavaScript has a method to do that, but I just resorted to doing it by hand instead. So I did that. Yeah, I'm gonna refactor this now. So what are we doing here? Let's add a comment. Calculate loop size of card. Okay, so while there's no results, result is value. Oh, while result is not equal to public key card. Okay, I guess we could I guess I could say this is true. While true, then I can get rid of result. I can get rid of this down here. I still need to push the values. And I need the loop size of card. We're gonna start at 0. We're gonna add 1. And loop size card. Yeah, thank you for joining me, Wilfred. Nice to see you. If you want to stay in touch, I'm _maximization on Twitter. So feel free to send me a message. Yeah, thank you very much for sticking around. Appreciate it. Have a nice Christmas. I hope you have a wonderful holidays with your family and friends. Enjoy this wonderful time of this less wonderful year. Hopefully 2021 is going to be a better year. Let's keep our fingers crossed. That's the subject number. This is all right, getting the values, and then we push the value while true if value equals public key card, then we break out of loop, and otherwise we push it. Will this still work? No, yeah, still works, great. And let's subject number remainder. All right, so we have the I'm thinking, do I need to keep track? I don't need all the values, I just need the previous value. So what I could do is I can say previous value is going to be 1, and I can use previous value in here, and then instead of pushing, I'm going to assign previous value to value. Is that going to work? That's going to work. Right, so we got rid of that array. Previous value will start with 1, or we can just say value, let value is 1, and then we could say, let's rename this one to new value is equal to public key card node, then value is new value. Okay, awesome. Yep. Still works. Okay, pretty happy about this. Let's go on to the next loop. Here we calculate the encryption key. So let's add a comment. Calculate encryption key. And then we have the loop size of the card. Well, I is smaller or equal than loop size of the card, and we're gonna stick with I here, and then maybe do the same thing as before. There's gonna be value. There's gonna be encryption key. And we're gonna start with 1. And we're gonna say encryption key times public key of the door, and then we get new encryption key, new encryption key. So we can just assign this to that, I guess. Will that work? Encryption key start with 1, encryption key times that, whatever is the new encryption key, and then our next iteration we're going to use that. Yep, that looks good. Still works, awesome. And then we have the answer for part 1. Yeah, I'm pretty happy with this. What we have here, I think. Encryption key, and then I plus plus, and then the loop size of the card. We start with value. Maybe how about what I can do is this value equals to new value. I can get rid of this, and while value is not equal to public key card, then continue, and I also can get rid of that. Will that also work? Yeah, it does. So this looks much better now. We refactored to while loops, really short loops, and that's basically the answer for part 1. That's it. And here, yeah, we're using the public key door, we're using the public key card in here. Yep, that's it. I'm gonna add this, and let's see, get status, oh, we have the example input. I usually do not commit the example input, so let's delete that. Git add, git status, git push origin main. Oh wait, commit first, commit day 25 solved. Woohoo! Yay, the last day of advent of code. We did it. Git push origin main. And it should appear in here. Yep, day 25. Yep, so that's it. We refactored a little bit, and we committed and pushed our solution to the remote repository. You'll find the link to it in the description below if you're watching this on YouTube, or otherwise it's in the chat on Twitch. And I think I'm going to have to conclude for today. Yeah, because there is no part 2, because we only needed 49 stars. The reindeer that just came from the North Pole brought our last star that we needed, so part 2 is there is no puzzle there, but I will go on and finish the remaining 2 stars that I have left to collect, and I will push those solutions to the repository as well. In case you want to look later, keep an eye on this repository. I'll have the solutions there, and then I'll have finished Advent of Code 2020. Thank you very much for watching so far. If you've been watching previous streams or previous videos on YouTube, thank you very much. I hope you learned a thing or two by watching me think out loud about solving this in JavaScript and how I approach a certain problem and how I reason about certain stuff. Some days have been more difficult than others. I haven't been able to solve all the days in the stream. I think a few I had to solve them outside of the stream, but most of them I managed to get them to solve them within the stream's time, so that was nice. And if you wanna stay in touch with me, I'm _maximization on Twitter. You can also find my website, maximorlov.com, where I write articles about generally about deploying applications, and it's targeted for Node.js developers, backend developers, JavaScript ecosystem. So if you're a JavaScript dev, front-end, back-end, working with Node.js or JavaScript, you might find some of the stuff that I write about interesting. I'm also creating screencasts on YouTube, and I occasionally stream as well. So yeah, I hope to see you in the future of one of the future streams. And with that, I'm going to wrap up, and I wish you a wonderful Christmas and a happy new year, a great 2021, a better 2021. Hopefully things are going to go back to normal, and yeah, thank you very much.